Hi, I'm Carson Lawrence. I'm the chief engineer, and we are
the Space Cowboys!
Hi, my name is Spencer Lampkin. I'm the project manager for the Space Cowboys, and this is our team. Here on the Space Cowboys, we're composed of a 29-member team made up of all undergraduate classifications. And this is the payload subteam.
Hi, my name is Chase. I'm the payload subteam lead.
Hi, I'm JP Person. I'm on the payload subteam.
And I'm Skylar Taggart, also on the payload subteam.
Moving over here, I'm going to introduce you to our simulation subteam.
Hi, I'm Lex Bradley. I'm the simulation subteam lead.
Hi, I'm Nirmal Bhatt.
And I'm Corinne Guerra.
And this is our structure subteam.
Hey, I'm Ryan Cobb, structure subteam lead.
Hi, I'm Chris Anderson.
I'm Grace Williams. I'm Marilyn Armstrong. I'm Lindsay Saunders.
I'm Alex Leeser.
I'm Brian Brinkley.
I'm Carly Foss.
I'm Ben Davis.
So this was our team. Now I'm going to bring you upstairs and we're going to go talk about the rocket.
So this is the rocket that we will be using to fly in the Argonia Cup 2019. It's actually a subscale for a larger rocket we're going to be using to fly in the Spaceport America Cup in 2019. It's named Arcus after a character from Greek mythology. It's about 6 feet long, about 3 inches in diameter. It's a full carbon fiber pre-preg airframe with a fiberglass payload section and a 3D printed nose cone. It will be flying on a K impulse motor. And now I'll let the sub-team leads take you through some of the more detailed design aspects.
This year, the motor we'll be using for our Argonia flight is a Cesaroni K780 Blue Streak motor. It's housed in a 54mm 5-grain reloadable casing. It has a maximum thrust of 228 pounds and burns for 2.7 seconds. In our rocket, this leads to a thrust-to-weight ratio of 18:1 and a rail exit velocity of 105 feet per second. Our rocket's maximum Mach number will be Mach 1.1, which will occur around 1,600 feet AGL. The rocket will continue to coast to an apogee of around 9,000 feet AGL.
Before you today, we have Arcus, which is a beautiful one-stage rocket just coming under 70 inches in length. Outside of 2 aluminum couplers, one here, everything you see was entirely made in-house. We have a 20-inch, 3-layer, 90-45-90 carbon fiber tube. We have a phenolic motor mount here that is mounted into this tube using 2 PLA 3D printed parts. We have a trapezoidal fin set, 4 fins, 60-degree sweep, 6.5-inch root cord length. Coming to the middle here, we have a 30-inch carbon fiber tube, same configuration as this one down here. Close to this aft section of this tube, we're going to have an avionics bay that is 3D printed, put in here with set screws, has U-bolts coming out either side, parachutes either side, main, aft, drogue forward, a dual deployment system. And up here, we have a fiberglass section, 12 inches long, that is used for RF transparency of our systems. And then here, we have a conical nose cone, straight triangular cone, 3:1 LD ratio. This was also printed in-house with PLA.
Our rocket uses a dual deployment system. It operates using double redundancy Altus Metrum Easy Mini flight computers, and they're housed within this casing, which protects them from the flight environment. In addition to the flight computers, we operate a single Altus Metrum telemetrum system, which gives us data acquisition and GPS location throughout the flight. One of the primary scientific payloads of a rocket is the supersonic pitot tube system. So this system is housed within the nose cone, and this stainless steel rod here allows the pressure to move from the outside of the rocket inside in a controlled manner where we can measure the pressure and then run some calculations and determine flight Mach number throughout the entire flight envelope. Finally, for the Argonia Cup, we are flying a system that we have called Yeet. It is an autonomous system that recovers separate from the rest of the rocket. It houses the golf ball as required by the Argonia Cup competition and is ejected at apogee alongside the drogue chutes where it falls back to the ground. The main design philosophy behind Yeet is for it to fall as quickly as possible to the ground to minimize wind variance and drag. So in order to improve its safety, it contains a separate recovery and avionics system. So it has its own parachute system as well as its own independent, fully functional flight computer. Yeet falls from apogee at about 9,500 feet to about 500 feet at about 200 feet a second. And at that 500-foot mark, it will deploy the parachutes and slow to about 20 feet per second and land safely.
All right, 3, 2, 1.
1.8 did it.